Welcome to the Processing Big Data module. This introduction section describes the content of this module. This module builds on the ingestion and storage elements of the big data pipeline that previous modules covered. This module highlights the processing frameworks that are integral to the AWS services that support big data processing in the AWS cloud. The objectives of this module are presented across multiple sections, each with its own video. The module wraps up with a sample exam question. This section introduces concepts for processing big data. Up to this point in the course, you have learned about the roles that ingestion and storage play in the pipeline. You also learned how closely related they are to the processing phase of the iterative data pipeline. Data frequently flows between the processing and storage elements. Raw data is ingested, stored, transformed, and processed. That data often returns to storage in a new format, and that formatted data is used for analysis and visualization. In this module, you will learn about some of the common frameworks for processing big data and the services that are used to process data for your analytics and machine learning, or ML, pipelines. In the Design Principles and Patterns for Data Pipelines module, you learned that components in the data processing layer are responsible for transforming data into a consumable state. The processing layer provides purpose-built components that enable a variety of data types, velocities, and transformations. Each component can read and write data to both Amazon S3 and Amazon Redshift in the storage layer, and all can scale to high data volumes. This architecture supports multiple ETL or ELT pipelines that perform iterative processing of data for different types of preparation and consumption. Each pipeline reads data from the storage layer, processes it using temporary storage as needed, and then writes it to the appropriate location within the storage layer. This module focuses on the big data processing aspect of this architecture. Batch data processing typically involves querying large amounts of cold data, or data that is infrequently accessed. With batch processing, it might take hours to analyze data to get answers to business questions. For example, you might use batch processing to generate a billing report at the end of the month. Batch processing jobs typically must scan all their new input data. Therefore, they can tolerate data that has only partial or no structure. Batch processing jobs can also compute results that are derived from all the available data, so they enable deep analysis of big data sets. Additionally, you can use batch jobs to compute the same query over different data sets. Hadoop MapReduce-based systems, such as Apache Hadoop and Amazon EMR, are examples of platforms that support batch-based data processing jobs. Streaming data is generated continuously by thousands of data sources. These sources typically send in the data records simultaneously and in small sizes. Streaming data includes a wide variety of data, such as log files that are generated when customers use your mobile or web applications, e-commerce purchases, in-game player activity, and information from social networks. Streaming data can also come from financial trading floors, geospatial services, and telemetry from connected devices or instrumentation in data centers. This data needs to be processed sequentially and incrementally on a record-by-record basis or over sliding time windows. The data is used for a wide variety of analytics, including correlations, aggregations, filtering, and sampling. Information from such analysis gives companies visibility into many aspects of their business and customer activity. For example, streaming data can provide information about service usage from metering or billing, server activity, website clicks, and geolocation of devices, people, and physical goods. This information can help companies to respond promptly to emerging situations. For example, a business could track changes in public sentiment on their brands and products by continuously analyzing social media streams and respond in a timely fashion as the necessity arises. Streaming data processing is beneficial in most scenarios where the new dynamic data is generated on a continual basis. Stream processing applies to most industry segments and big data use cases. Companies generally begin with simple applications, such as collecting system logs, and rudimentary processing, such as rolling min-max computations. Then, applications evolve to more sophisticated, near real-time processing. Initially, applications might process data streams to produce simple reports and perform simple actions in response. For example, alarms could be emitted when key measures exceed certain thresholds. Eventually, those applications perform more sophisticated forms of data analysis, such as applying ML algorithms and extract deeper insights from the data. When you launch your cluster, you choose the frameworks and applications to install that best fit your data processing needs. Frameworks are the data processing engines that are used to process and analyze your data. You can select frameworks based on whether your data processing is batch, interactive, in-memory, streaming, or something else. Hadoop and Spark are the two most common frameworks that Amazon EMR uses. You can use applications to create processing workloads with higher-level languages, use ML algorithms, make stream processing applications, and build data warehouses. Many frameworks are available for processing big data, and new frameworks and enhancements to existing frameworks are released with increasing frequency. A single framework will probably not meet all of your big data analytics needs, so it's common to use combinations of processing frameworks. The table on the slide displays a number of popular frameworks for processing big data. The frameworks are organized by the use case type of batch or stream processing that each framework is best suited to support. Some of these frameworks have been previously discussed in this course, while others will be covered in this and subsequent lessons. Here are a few key points to summarize this section. Big data processing is generally divided into two categories based on data type: batch and streaming. Batch data typically involves infrequently accessed cold data, and analytics workloads often involve longer processing times. Streaming data involves numerous hot, or frequently accessed, data sources. The data must be processed in a sequential and incremental fashion. Batch processing and stream processing each benefit from specialized big data processing frameworks that are tailored to their processing needs. This section introduces the Apache Hadoop processing framework. Hadoop is an open-source framework that uses a distributed processing architecture, mapping tasks to a cluster of commodity servers for processing. Hadoop consists of four main components: Hadoop Distributed File System, or HDFS, yet another resource negotiator, or YARN, MapReduce, and Hadoop Common. Hadoop clusters consist of main nodes and worker nodes. In this format, main nodes are responsible for orchestrating jobs, while worker nodes are responsible for processing those jobs. With Hadoop, you can store as much data as you like. You aren't required to pre-process data prior to storing it. Therefore, the framework provides increased flexibility. Hadoop also has a high degree of fault tolerance thanks to node failover. If a node fails within a cluster, its tasks are redistributed throughout the other nodes within the cluster. Data loss is likewise prevented by having multiple copies of the same data stored throughout the cluster. The Hadoop infrastructure is scalable. As data processing and computing requirements grow, you can easily add nodes to support that growth in volume and velocity. Because it is an open source framework, Hadoop is free and capable of running on inexpensive hardware. Finally, you can use Hadoop to process structured, unstructured, and semi-structured data. You can transform the data into a variety of other formats to integrate with your existing data sets, and you can store the data with or without a schema. The framework does have a few challenges. Because of its open source nature, stability issues can arise as the framework is updated. You can avoid this challenge by running only the latest stable version. Hadoop also makes heavy use of the Java programming language, a commonly targeted language that can leave the framework open to vulnerabilities. Lastly, security concerns are inherent to Hadoop. Lack of authentication and encryption can lead to questions about the veracity of the data. The Hadoop Distributed File System, or HDFS, is the distributed file system of the Hadoop framework. You can use HDFS to store huge amounts of data for further processing. HDFS and the Hadoop cluster use a hierarchical node architecture, which consists of a single name node that manages multiple data nodes across clusters. HDFS is typically used by applications that have large data sets, so it's designed to provide high aggregate data bandwidth. To support data velocity while storing data, HDFS splits the data into small blocks, called data blocks, and stores these blocks across several nodes of the cluster. In the example on this slide, a large data file has been split into 3 data blocks. Each block resides in a different data node when possible. To avoid losing data if a cluster node fails, HDFS replicates each block several times across different nodes. This enables a high degree of fault tolerance within HDFS. The number of times that a block is replicated is called the replication factor, and it's a configurable setting. The cluster's name node catalogs the metadata about each file that is stored in the cluster. The cluster data nodes store the data blocks for each file that has been saved to HDFS. Yarn is a large-scale distributed operating system that is used with Hadoop. Yarn makes the data that is stored in HDFS accessible for different processing. Yarn dynamically coordinates the use of available Hadoop resources to schedule and perform that processing. Yarn has a few primary components. The resource manager controls the use of resources within the Hadoop cluster and manages the containers that are launched on each cluster node. The resource manager has 2 main components: the scheduler, which allocates resources to the running applications based on the resource requirements of those applications, and the application manager, which accepts job submissions, negotiates the first container to run the application leader, and provides the service to restart the application leader on failure. The node manager controls the use of resources within a single Hadoop cluster node and monitors the containers that are launched on that cluster node. The application leader works with the resource manager and node manager to acquire cluster resources for processing tasks before running and monitoring those tasks. Containers are collections of cluster resources, such as memory and compute, that are allocated from a single cluster node to perform assigned processing activities. MapReduce is a framework for processing large datasets with a parallel distributed algorithm on a cluster. Hadoop MapReduce simplifies writing parallel distributed applications by handling all of the logic, while you provide the map and reduce functions. The map function maps data to sets of key-value pairs called intermediate results. The reduce function combines the intermediate results, applies additional algorithms, and produces the final output. If you use HDFS to store your data, Hadoop automatically splits your data when it is stored in the HDFS cluster nodes. However, if you use Amazon S3 to store your data, Hadoop splits the data by reading your files in multiple HTTP range requests whenever a processing job is started. The split size that Hadoop uses to read data from Amazon S3 varies depending on the Amazon EMR version that is being used. The split size is generally the size of an HDFS block when operating on data that is stored in HDFS. Larger numbers provide less task granularity, but also put less strain on the cluster name node. In the example on the slide, we see a 500 megabyte file and 8 mapper processes that are available to process the data. Big data processing needs to maintain pace with the volume and velocity of data. So in this instance, the 500 megabyte input file will be split into 4 smaller files. Each of these files will use an available mapper for processing in parallel. Let's take a look at some of the more common frameworks that work with Hadoop to process batch data, streaming data, or both. Apache Flink is a streaming data flow engine that builds real-time stream processing for big data applications. Flink performs transformations on data sources such as Amazon Kinesis data streams and Apache Cassandra databases. Flink also has connectors for third-party data sources, including Kinesis data streams, Apache Kafka, and others. Apache Hive is an open-source SQL-like data warehouse solution that runs on top of Hadoop. Hive offers some limited data warehouse capabilities and is a familiar programming model, making it an attractive option for big data analysis. Apache Presto is an open-source, distributed, in-memory SQL query engine that was originally developed by Facebook. Though the engine is similar to Hive, Presto emphasizes faster querying specifically to perform interactive queries. Presto doesn't run on MapReduce. Instead, the engine operates in memory and is based on its own engine. Apache Pig is a simple, high-level, textual data flow language that uses parallel processing to perform analysis on large datasets. Here are a few key points to summarize this section. Hadoop includes its own distributed storage system, Hadoop Distributed File System, or HDFS. When you store data in HDFS, Hadoop splits the data into smaller data blocks by using the MapReduce process. MapReduce processes large datasets with a parallel distributed algorithm on a cluster. MapReduce splits jobs into discrete tasks so that the job tasks can be run in parallel. This section introduces the Apache Spark processing framework. Apache Spark is an open-source, distributed processing framework that was created to address the limitations of MapReduce. Spark processes data in memory, reduces the number of steps in a job, and reuses data across multiple parallel operations. With Spark, only one step is needed, where data is read into memory, operations are performed, and the results are written back. This results in much faster processing. Spark is a cluster framework and programming model for processing big data workloads. When you run Spark on Amazon EMR, you can use EMRFS to directly access your data in Amazon S3. Spark supports multiple interactive query modules, such as Spark SQL. Spark also reuses data by using an in-memory cache to speed up ML algorithms that repeatedly call a function on the same dataset. This dramatically lowers the latency, which makes Spark multiple times faster than MapReduce, especially for ML and interactive analytics. In Spark clusters, Spark applications run as independent sets of processes. The Spark context object that resides within the driver program coordinates these processes. Spark connects to a cluster manager, which acquires executors from nodes within the cluster. These executors are responsible for running the computations and storing the data in cache for your application. The Spark context object communicates directly with the executors, sending them tasks to be processed. The components that make up the Spark framework are Spark Core, Spark SQL, Spark GraphX, Spark Streaming, and Spark ML-lib. Let's take a closer look at each of these. As the name implies, Spark Core is the foundation of the platform. It's responsible for memory management, fault recovery, scheduling, distributing and monitoring jobs, and interacting with storage systems. Spark Core is exposed through APIs built for Java, Scala, Python, and R. These APIs hide the complexity of distributed processing behind simple, high-level operators. Spark SQL is a distributed query engine that provides low latency, interactive queries up to 100 times faster than MapReduce. Spark SQL includes a cost-based optimizer, columnar storage, and code generation for fast queries while scaling to thousands of nodes. Spark GraphX is a distributed graph processing framework that is built on top of Spark. GraphX provides ETL, exploratory analysis, and iterative graph computation to enable users to interactively build and transform a graph data structure at scale. It comes with a highly flexible API and a selection of distributed graph algorithms. Spark Streaming is a real-time solution that uses Spark Core's fast scheduling capability to do streaming analytics. Spark Streaming ingests data in mini batches and enables analytics on that data with the same application code that is written for batch analytics. This improves developer productivity because they can use the same code for batch processing and real-time streaming applications. Spark ML-lib is a library of algorithms to do ML on data at scale. Data scientists can use R or Python to train ML models on any Hadoop data source, save them using ML-lib, and import them into a Java or Scala-based pipeline. Here are a few key points to summarize this section. Apache Spark addresses some limitations of Apache Hadoop by performing processing in memory, reducing the number of steps in a job, and reusing data across multiple parallel operations. Spark reuses data by using an in-memory cache to speed up ML algorithms. Spark uses a collection of objects in cached memory, known as data frames. This section introduces the Amazon EMR service. Amazon EMR is a managed cluster platform. The service simplifies running big data frameworks such as Apache Hadoop and Apache Spark on AWS to process and analyze vast amounts of data. By using these frameworks and related open source projects such as Apache Hive and Apache Pig, you can process data for analytics and business intelligence, or BI, workloads. Additionally, you can use Amazon EMR to transform and move large volumes of data. You can move this data in and out of other AWS data stores and databases, such as Amazon S3 and Amazon DynamoDB. With Amazon EMR, you have the ability to launch clusters in minutes, deploy multiple clusters, and resize clusters that are already running. By using these clusters, you can process your large volumes of data in a cost-effective manner. Amazon EMR relies on HDFS and Amazon S3 for storage. Therefore, you can store input and output data in Amazon S3 while using HDFS to store your intermediate results. Finally, Amazon EMR provides the ability to perform automated installations of common big data projects such as Hive, Pig, and Spark, and run applications such as Hadoop, Spark, and Presto. The central component of Amazon EMR is the cluster, which is a collection of Amazon Elastic Compute Cloud, or Amazon EC2, instances. These EC2 instances are referred to as nodes, and each node has a role, known as a node type, within the cluster. Each node type can have different software components, which further delineates its role in the cluster. Amazon EMR uses 3 node types: main, core, and task. The main node is responsible for managing the cluster by running software components that coordinate data distribution and tasks to other nodes for processing. Every cluster has a main node, and you can create single-node clusters that have only a main node. Core nodes are responsible for running tasks and storing data in your cluster's HDFS. Multi-node clusters must have at least one core node. Task nodes, which are optional, only run tasks. Task nodes don't store data in HDFS, and you can add them at cluster launch or add them to an already running cluster to increase processing capacity. Additionally, you can terminate individual task nodes to reduce costs when they are no longer needed. Several layers make up the Amazon EMR service architecture. Each layer provides specific capabilities and functions to the cluster. The storage layer consists of the different file systems that are used within your cluster, such as HDFS and EMRFS. This layer also includes the local file system of any locally connected disk. Each EC2 instance within the cluster has pre-configured block storage, known as an instance store, which persists for the duration of the instance's existence. The cluster resource management layer is responsible for managing your cluster resources and scheduling data processing jobs. Yarn is the default management component that Amazon EMR uses. Note that this doesn't mean that Amazon EMR clusters are restricted to Yarn. Many frameworks and applications that are offered in Amazon EMR don't use Yarn as a resource manager. In the data processing frameworks layer, the main processing frameworks are Hadoop, MapReduce, and Spark. The applications and programs layer is where the applications that were discussed earlier in this module provide capabilities such as using higher-level languages to create processing workloads, using ML algorithms, making stream processing applications, and building data warehouses. In addition, Amazon EMR also supports open source projects that have their own cluster management functionality instead of using Yarn. When you launch your cluster, you choose the frameworks and applications to install for your data processing needs. To process data in your Amazon EMR cluster, you can submit jobs or queries directly to installed applications, or you can run steps in the cluster. You can submit jobs and interact directly with the software that is installed in your Amazon EMR cluster. To do this, you typically connect to the main node over a secure connection and access the interfaces and tools that are available for the software that runs directly on your cluster. You can submit one or more ordered steps to an Amazon EMR cluster. Each step is a unit of work that contains instructions to manipulate data for processing by software that is installed on the cluster. This slide illustrates an example process that uses 4 steps. Submit an input dataset for processing, process the output of the first step by using a Pig program, process a second input dataset by using a Hive program, and write an output dataset. Generally, when you process data in Amazon EMR,